everyone. Thank you for being here. I know it's not an easy time right after lunch. And I really appreciate you being here today. I know you had other options, and I'm not a flight attendant, but being here in Lugano in this beautiful place, I really appreciate you being here. My name is Gil, and I'm going to talk about in-network computing, which is something that we do at Mellanox. I'm only going to talk about one example of in-network computing, what we call shrub. I'm going to talk about the technology, why we think it's important, and how you can actually use it. I'm focused currently on the software part of this technology. And I had to brag, okay? Before we go into technology, this is where we stand today. We accelerate the 3 top supercomputers in the top 500 list. 2 of them are part of the Coral, the DOE systems, one in Oak Ridge National Lab and the other in Livermore. Both are using the same technology with somewhat a different configuration. One of them is more focused on GPUs. The other have a different mix and match of CPUs and GPUs, but they are both accelerated with the same interconnect coming from Mellanox, and are both a result of collaboration between IBM, Nvidia, and Mellanox for the past few years. The third one is a totally different technology. It's the Wuxi supercomputing using a Chinese CPU, using a totally different system. And the important part, they're all accelerated by Mellanox Interconnect. And with that, I'm going to move to technology. So what is a Mellanox Interconnect? Why is it different than the other options? Why is it different than Omnipath from Intel or from Ethernet? And I'm not going to talk about all the details and all the different things that are different, but about the ideas behind what we're doing. And the main difference here is that if you look at the old way of doing interconnect or the old way of building systems, you would have processing engines. Those can be CPUs, GPUs. Today you will even see people accelerating applications with FPGAs or domain-specific ASIC, mostly in the area of AI, but there are other solutions for different applications. And they would be connected by some interconnect. You have to connect them, okay? We are talking about supercomputing using distributed computing, so you need connectivity. But everything was dependent on the CPU or processing engine. The interconnect was allowing you to move data from one point to another, but the CPU would drive this data movement, is responsible for everything and every part of this data movement, and of course is responsible for all parts of processing this data. And when we look at the system, we see a totally different opportunity or a totally different solution and system. We look at the entire system in a more holistic way. We try to remove the boundaries that we were used to, where CPUs are doing processing, software is responsible for moving the data from one point to another, and the interconnect is a connectivity between the servers. We look at the entire system in a more holistic way and see opportunities for doing things differently, doing a new co-design between software and hardware, a new code design between end nodes and interconnect. And within those opportunities, we see a very good opportunity for doing things with the data as it traverses the network. We implement all kinds of technologies. We will not have the time to discuss all of them. We will focus on this one, shrub. But again, what we're actually trying to do at Mellanox, and this is more of a vision, and I'm not going to get into the details of each one of those features. We started with connectivity. We need to connect, and we support all kinds of topologies. Again, we don't have the time to discuss those. We then started offloading the networking part. So we have implemented fully offloaded transport. If you compare that to TCP, where the TCP stack relies in the kernel, or there are some user-level TCP, all the transport is implemented in Mellanox hardware. There is no transport part being done by software, which allows you to do things in a better way. And then we added RDMA, which allows you to move data faster and in a more efficient way, removing the CPU from the data path, with GPU Direct doing exactly the same for GPUs, and more things we did within the transport and networking layer. And once we were sort of done with that, we moved to the next mission, and that's looking at the communication framework, not the TCP level, but the MPI, SHMEM, or other communication levels. And we started offloading communication operations. And with that, we had good opportunities to accelerate more, things you cannot do at the transport level, and I'll talk about that later. And we have now started looking into the application frameworks and see where application level operations make sense to be offloaded into the network. And again, we are now looking at specific applications, but we see that there are very nice opportunities which are shared between many applications, many application domains. So let's start about Sharp. It was first built for HPC. We looked at HPC as the first market, and it was done to accelerate MPI operations. This is a part of the MPI communication frameworks focused on MPI, to reduce the time of the operation, to remove the CPU or GPU from the operation, so now the CPU is free to do other things, and enable overlap with that. We started that a few years ago, and then the AI hype came, and we just realized it makes a lot of sense. The exact same technology is very important for distributed AI, and I'll give a few words about that later today. So we're talking about all-reduce operation. I assume everyone here is aware of what all-reduce is, right? If not, just let me know and I'll... Okay. So either you didn't have enough coffee or you all know all-reduce. I'll assume the second. So there are multiple ways to implement all-reduce. We all know the tree-based way. Actually, it's probably the most common implementation in different MPIs today. Sending data within a group into a single node, which will reduce the data, and then doing that in hierarchies, so you don't have too large number of sources sending to a single destination. Doing that in a tree, you have a nice implementation, multi-stage implementation, moving the data multiple times to do all reduce, and then you need to somehow broadcast, and you can do that either with exactly the same tree, or implementing that with some hardware multicast, like some of the network technologies offer. But again, it's a multi-stage, pretty good implementation for all reduce. Another one would be recursive doubling, which is sort of a tree with a binary tree. And again, it's logarithmic. You move the data more than once. It's a multi-state operation, giving pretty nice results. But then we came with this new technology saying, okay, so you're sending the data into the switches, right? You have to do that to reach your peer end node in the algorithm. The switches actually sees all the data anyway. Why not just reduce the data within the switch? This is the only component in your network that can absorb data from multiple sources in a good and efficient way, because this is what switches are doing. They have a large number of ports. Each one of them is capable of full wire speed transmission and receiving of data. It's already connected to your end nodes. It makes a lot of sense to just reduce the data while it traverses the switch and move less data. But then the switch doesn't see all the end nodes. This is an example of sort of fat tree topology with switches connected to end nodes and connected physically to have multiple layers of connectivity to connect a large number of end nodes. So a switch is connected to a subset of your end nodes, but it's also connected through another switch to those other leaf switches. This is how factory works. This is just an example. And then what you could do is build an hierarchical tree between those switches and do the reduction in the network. And this is what Sharp is, basically. Looking at the picture, we have to move the data and we have to aggregate the data. We do that. Each switch is responsible for a subset of the end nodes. They are all working in parallel on the same layer. Next layer aggregates data from multiple switches, and if you have a very large number of nodes, you will have more than 2 layers of switches, so you will do the aggregation in the switches. It was designed as flexible as possible to do this reduction, and it does 2 things. It reduces the data, and it enables the broadcasting of the result to all the end nodes. It was built with the vision of HPC, so it's very much similar to MPI's API. It supports the data types important for MPI and the operations. Add like sum, min, max, min lock, max lock, all the operations supported by MPI. And later, when we saw the opportunity for AI, we added the support for 16-bit floating points and some other interesting capabilities that are not supported in MPI, but are very useful and very important for deep learning. And with that, we have a full solution for doing reduction in the network. So if you look at the switch, it now have floating point engines doing mathematical operations, logical operations. So now the switch is actually sort of a processing engine. It is like a coprocessor for the CPU, GPU to do the reduction in the most efficient way, and it's not because we know how to do floating point faster than any CPU or GPU company. We don't. Both Intel and Nvidia and AMD and ARM and all those CPU companies, they know how to do the most efficient floating point engines. We do not compete with them in that. What we do have is the opportunity to be in the right place. What we have is the opportunity to implement this floating point engine within the switch hardware where you already have access and see all the data in a very efficient way. That's the difference. We do not do floating point operation faster or more energy efficient than any other CPU vendor or GPU vendor. That's not where we try to compete. So again, if you look at what's happening within the network, if you do, sorry about that. If you do, okay, here it is. If you do recursive doubling, you will have 2 steps. In the first step, okay. In the first step, you have data moving between subset of the end nodes, and then you have the next step. But in Sharp, you only have 1 step. You do the aggregation within the switches as the data goes up, and you broadcast the results as the data goes down. That's it. There is no way to do a more efficient reduction than doing that within the network. So some numbers. How good is it? If you have a small number of nodes, recursive doubling is good enough. If you have 2 nodes, you will get exactly the same result, or almost the same result. The benefit comes as you grow. And the nice thing here, this is for small message sizes with increasing number of nodes within the cluster doing all-reduce operation. This is a simple all-reduce benchmark showing that if you implement that in software, and this is a software that we are very proud of. I'm not comparing to some bad MPI implementation. This is the Mellanox best MPI implementation for all-reduce. But still, as you grow the number of nodes, the latency of all-reduce grows because you need to do more iterations or more steps in your algorithm. And there is no way to avoid that. But as you do that in the switches, the latency stays almost flat. what you see here when moving from 8 to 16 nodes is moving from one switch to 2-layer switches. We could do that in a single layer because the switch has enough radix, but we wanted to show this phenomena of when you move from 1 layer to 2-layer factory, you have an increase of about 150 nanoseconds. But then as long as you stay with 2 layers, which allows you to do more than 1,000 nodes, you are with flat latency. Once you move to 3-layer, you will see yet another step of about 150 nanoseconds, and now you stay flat for as far as you can go with 3-layer factories, which is quite a large number. This one is for larger messages, but again, it's the same phenomena. Flat latency when you stay within 1 layer, and then a small growth on latency. This one shows you quite a larger scale, which is not what I wanted to show. The important part here is this was a benchmark done on a Dragonfly topology, so it's not factory. I wanted to show we are not limited to factory. Yes, the example was factory. It's easiest to see how trees are built on factories. We know how to build those logical tree of sharp on top of any topology you would like to use. And when going to Dragonfly Plus, this is in Canada, a cluster of about 1,500 nodes. Again, you see similar phenomena. It's not as flat as in factory, but still you see the difference between software implementation and the hardware implementation within the network for different methods. Oh, no, this one is for 1,500 nodes, 1 process per node, and this includes 40 processes per node. So you have some additional latency for doing the reduction within the node and for distributing the data within the node. We do that in some hierarchy. But again, the important part, sharp works on any topology you would like to use. Let me skip this one. So how does sharp works? Basically, we start sending data. The end nodes send data to the switches. The switches will have to log this data and then get more data from another end node and log the data, and only then the switches can do the reduction. And the main reason for that is that A plus B plus C does not equal A plus C plus B for floating point, unfortunately. It means we do need some resources within the switches. So we have implemented those resources, and I'll talk about the difference between short messages and long messages. For short messages, you need to keep the data coming from your sources until you have the data from all the sources before you can start the aggregation. Actually, I'm lying. You can hold half of it. We have a trick to do that. But you do need to log the data until you can do the operation. Otherwise, it will give you different results if the data is coming in different order. Once calculated, it goes up the tree. And let me try and skip some of the animation, but you will get, let's see, okay. It will not skip, unfortunately. Yes, it will. Okay, so now the root of the tree has all the data needed, all the data from its sources. Now it's being switches that have already aggregated the data from the end nodes. And we can start sending the results. And we actually use the same tree to distribute the results, sending the data to all the end nodes. And the nice thing about using this tree is that what I didn't say is that those connections between end nodes and switches, as well as switches and switches, are all implementing the InfiniBand transport in hardware. So there is full reliability implemented in there. If packets are being discarded, the hardware knows how to do the retransmission and how to check for correctness of the data. So once you distribute this data, everything is reliable and get to the end nodes. You do not need to implement software reliability on top of that. That's the only broadcast or multicast implementation today that works on large scale in a reliable way. To make that work for AI or for some of the HPC applications, we have integrated that together with GPU Direct technology. Anyone familiar with GPU Direct technology? Okay, 2. So 2 knows GPU Direct. Some of you did not have coffee and the rest don't know GPU Direct, right? So the way GPUs work, GPU is an accelerator. It's not like the CPU. It doesn't have the capability of doing communication. It doesn't run any OS. And for that, if a GPU wants to do some computation and then send the data to another GPU, because you are doing distributed computing, you have to move the data from the GPU memory to the system memory, to the CPU memory, and interrupt the CPU and ask the CPU to do the communication. That's the standard way, because GPU is an accelerator. It gets a kernel, run it, get the result, give it back to the CPU, and now the CPU is responsible for the data. We have been working with Nvidia for multiple years now to make sure that GPUs can do that in a more efficient way, because copying the data and interrupting the CPU is not the most efficient way to move data. And what we did is to allow the GPU to send data from the GPU directly through the Mellanox networking gear to a remote GPU. Combining that with shrub means that if a GPU now has the data and wants to do AllReduce, all it needs to do is send it to the switch and wait for the results. That's it. So GPU Direct now works between GPUs and Mellanox switches. The GPU sends the data to the switch to do the reduction and receive the results directly from the switch. No CPU involved in this work to get the most efficient result. By the way, how are we with the time? Yeah, not too bad. So now when we look at the result, we compared shrub to Nickel. Nickel is Nvidia's collective communication library. And we compared shrub results and Nickel to the latest from Nvidia to show the results of, in this case, this is a deep learning training of ResNet 50 neural network using ImageNet database. And what usually people compare for deep learning is how many images can the system process in a second. So this is images per second, Nickel without shrub and Nickel with shrub on 2 different systems. So we show that accelerating AllReduce with shrub not just accelerate a benchmark. It's very easy to show AllReduce benchmark and show that we do that faster. That's not enough. This one is showing real training of ResNet 50 neural network with ImageNet database on a GPU systems with 8-node 16 GPUs and 8-node 22 GPUs. Unfortunately, this was the largest system that I had access to. Probably later this year, we will have access to more GPUs. And you can actually see a real benefit of offloading AllReduce from software to hardware. And again, we're not trying to show that Nickel 2 is not a good implementation of AllReduce. This is not the point. AllReduce implementation within Nickel is very good today. Actually, they just released the latest, the 2.4, which have very nice performance at scale. I'll show some numbers later. What it shows is that if you do things in the right place in your system, and not stay with the old way of doing everything within CPUs or processing engines, you can gain benefit in your application performance. A few words about software. I did hardware for many years and moved to software, so now I can talk about software as well. With HPCAC is Mellanox offering, software offering for HPC and AI. It covers MPI, SHMEM, UPC, all your frameworks required to run your HPC applications. I'll skip some because we don't have enough time. And the important part is we actually use Openmpi within our offering, our HPCAC package. It runs on top of our HCal, the collective library for Mellanox hierarchical collectives, which then calls shrub library. So shrub is a separate library today that runs on top of the InfiniBand network. And if you look at the entire system, maybe this is the more interesting part. As you know, InfiniBand is a software-defined networking technology. We hear about SDN for the past, I don't know, about 10 years from the Ethernet guys with OpenFlow and Open Networking and Open Summit and many new technologies that were trying to take Ethernet into the SDN, the software-defined networking world. InfiniBand was that the kind of technology for the past 20 years. It was defined as SDN technology, where you have subnet manager, a software entity managing your entire network, and allowing you to configure and do whatever you want on top of this network hardware. The network hardware that you buy has nothing to do with the software subnet manager running. You can take network hardware from one vendor and have your own software or get it from any vendor. And there are multiple implementations today of the subnet manager. If you get from different vendors, you will get different implementations of subnet manager. We push the Open Subnet Manager. It's an open source implementation. This is where we put our effort, but it's not the only implementation. So to that, we have actually added an aggregation manager, a new centralized manager that is responsible for all those new resources within the switches. Think about it. You had allocated resources for a job in manners of nodes, GPUs, CPUs. Now there is a new processing engine, there is a new resource that is not a part of the end nodes. It runs within your network switches. So we have added this aggregation manager, which is responsible for those resources, to make sure that if you run more than one job on the same cluster, sharing the same switches and the same networking, we wanted to make sure that first you have all the security that you need. You must have isolation between data of different jobs. We do not want the switch to add data from one job to data of another job and provide it to any of those jobs. So we have this isolation. I won't have time to get into the details, but we have this isolation. And the second is you do not want one of the jobs to get all those aggregation resources. We talked about the fact that we need buffers within the switch to hold that. And there are multiple resources, so we need to make sure that one job can only take the quota allocated to it and not anything beyond that. And the aggregation manager is the entity responsible today for managing those resources. We have some integration into job schedulers like Slarm to make sure that as a user, you don't need to know about this aggregation manager. You want to schedule a job into Slarm and you want Slarm to take care of all resource allocation and whatever needed. So we have the integration of the aggregation manager to Slarm today. And again, I'll skip some of the details and talk a bit about, so we talked about integration of Sharp into HPCX and our software, and that's obvious. Let's talk a little bit about Nickel. Nickel is Nvidia's communication library. We just compared Sharp to Nickel, which is a not fair comparison because it's a hardware implementation to software CPU-centric implementation, and of course hardware is faster. So Nickel, it started with GPUs. They have a lot of processing engine internally, which interconnect and communicate with the internal buses, which we don't have details of. And then Nvidia implemented Nickel. The first version was designed to allow communication between GPUs within a box. It was supposed to have all the tunings and everything that needed to utilize the NVLink, connecting those GPUs in the most efficient way, because NVIDIA have all the information and they can implement it the easiest. The second version was going out of the box and allowed connectivity between multiple boxes using RDMA as the basic technology to connect those GPUs. And the way it works, the first implementation was a ring implementation. Within a box, it would connect a ring between all the GPUs and do ring implementation of AllVideos. If you connect multiple servers, multiple boxes, it would cut the internal ring and connect that over the interconnect fabric. Again, RDMA-enabled fabric. You can use Mellanox or any other RDMA network adapters that are available. Of course, the Nvidia boxes, if you look at DGX1, they actually integrate Mellanox network adapters into the boxes. If you buy a DGX1, you get 4 network adapters internally. If you buy a DGX2 box, you have 8 of those network adapters, giving you 800 gigabit per second per server. The only problem is that ring implementation doesn't scale very well, so they went to the implementation of tree. What they did was building a tree between those boxes. Again, internally it's a ring, externally it's a tree. It's supported in Nickel version 2.4. And still, this provides the numbers that you can see from a tree implementation. You can see that in terms of bandwidth, this is ring performance, and this is tree performance, much better bandwidth. In terms of latency, much better latency, lower is better. And the main reason I'm showing that is not because I care about trees or trees versus ring. The nice thing is if you look at this number. This is the number of GPUs in this benchmarking. 25,000 GPUs in a single benchmark. That's the largest I've ever seen. It was run on Summit, the largest CPU today, the largest supercomputer today. But then if you go sharp, it scales much better and gives you much better performance. Unfortunately, we did not have the opportunity to test sharp on Summit yet on full scale. But the idea here is that instead of implementing the tree, all we have to do is we still leave the ring within the node on top of the NVLink. But then once you go out to a sharp tree. If you connect a DGX box, you will actually have 4 trees because each DGX box has 4 network adapters. So you can either connect them to a single larger tree or have 4 trees. Doing that, both will work. And showing numbers, this is the largest one that we could test. And actually, I didn't test it. I do not have access to this. Oh, sorry, this is the message size. Anyway, the numbers here came from Nvidia. They have tested it, and actually this slide was presented in the GTC 2 weeks ago, showing that with Sharp you get about 2x bandwidth compared to both ring and tree. Again, this is Nvidia's presentation. Well, this slide, not the entire presentation. So we have Sharp integrated into Nickel. It's not out yet. It's out as a demo. It's not generally available. It will be on the next release of Nickel 2.5. And again, showing a benchmark is not enough. This is ResNet 50, the same ResNet 50 that we showed earlier today. ResNet 50 neural network doing ImageNet training. And this is the benefit we could see on this small cluster that we had from Nvidia. And with that, some benchmarks. Again, the basic thing is latency is much faster. You get, for large messages, okay, so here's one thing I did not talk about, and I'll spend the next few minutes and leave at least 5 minutes for questions. We talked about storing data within the switches. We need to store data within the switches because we need to do the mathematical operations in the same order because A plus B plus C doesn't equal A plus C plus B. How do you do that if the message is, if you want to aggregate not 8-byte or 24-byte, you want to aggregate a few megabytes or even a gigabyte? If you look at AI training, the larger your neural network, the more complicated and deeper neural network people are using, will cause aggregation of larger tensors or larger vectors. How do you store that in a switch? And the answer is that a switch cannot store gigabytes of data. There is no way of doing that. So what we did was to implement a support for streaming aggregation. Instead of storing a gigabyte, all I need to do is store a few kilobytes. And then once I get those few kilobytes from all my sources and I can start doing the reduction and send up the results, I free up space and get more data from the end nodes. So how much data do I need to store? It all depends on how fast can I signal the end node to send more data. I need to make sure that I have enough data stored so that if I start freeing up space, sending this notification, it takes the network adapter some time to start sending this data, I still have enough data to do the reduction. And just to remind you, we do that in 200 gigabit per second today. This is the link speed, and I want to make sure that I take all the sources, do the aggregation, and send a result at 200 gigabit per second, which means I do 200 gigabit per second times the input to my switches of reduction. Pretty fast. And to do that, I need either very large buffers within the switch, and that's very expensive, or very fast flow control running between my switches and the sender. And again, if the sender was a software entity, you send him a notification, okay, I can get some more data. The latency it takes to software to realize that it can send more data and send this data is so large that I would have needed huge buffer within the switches. So again, the only way to implement this kind of mechanism is to have hardware offload for this flow control, so the network adapter, it already sees the entire 1 gigabyte vector. It will send a portion of that to the switch. The switch will signal, okay, send more data. It will send more data and do that in nanoseconds latency and not microsecond latency as it would take any software implementation to do that. So again, the only way to do that is using hardware mechanisms, hardware accelerators. And this is showing the benefit of streaming aggregation and not just small messages. We can stream data at 200 gigabit per second from each end node to a switch, aggregate this data, forward it to the next switch, and do that as we utilize the full 200 gigabit per second. Again, another comparison of doing that with ResNet 50, that's my, I really like ResNet 50. So, and with that, thank you.